Okay. So our second one here, I'm definitely going to have to draw. Okay, so we've got a power line with a line running, and that's 7 meters. And then below it, a farmer has a 2 meter high and some length. So it's got a coil of wire. That's a rectangular coil that's 2 meters by some length. And there's 10 turns of coil there. So the 10 turns are going into and out of the page. Okay. And through this line, there's a current running. And it's actually a sinusoidally varying current. So our current is actually I naught sine omega t, where omega is 2 pi f, and in this case f is 60, so 2 pi times 60 per seconds. So that is that's our frequency for our current. And so we're going to get a B field that's emanating from this line, which is going to pass through our loop. Which is going to pass through our loop at different intervals, and so we're going to get a changing flux and therefore an EMF generated in the coil. The question asks, we need 170 volts in the coil, so for what L, so what length of our coil would we need to generate a voltage of 170 volts? And also it needs to be 60 hertz varying, but we'll find that will just come out from the current itself being 60 hertz varying. Okay, so how are we going to approach this? Well, to find a voltage that's induced, we're going to need to use Faraday's law, so minus d phi by dt. We have actually not one coil, but 10 coils. And so we're actually going to use kind of the coil version of this, which is n d phi by dt. So the n here, I'm just going to put an arrow instead of an equal, just because I'm doing it for coils. So both of these should be equivalent, but here this phi is referring to a single coil, while this phi would be referring to all the coils. But I'm just going to use this guy. So what is our flux? So let's find that first. So now to find the flux, I'm also going to kind of redraw the relevant parts. So here is my coil, which is 2 meters high. And actually that doesn't matter for me too much. I'm going to leave that out. But here's my line, which is 7 meters high. And I'm going to get a B field at the very tip, which is at 5 meters. And I'm going to also get a B field that's at the very base, which is going to be 7 meters. Okay? Now, the length is L, and my B field from a conducting line can be found as mu naught I over 2 pi r. So it is an r-dependent B field. But my flux is typically defined as B dot A. But in this case, I'm going to define it as d phi is B dot dA. So some incremental flux is B dot dA, where now my dA is going to be for a small area of length L and width dr. And then I'm going to integrate it from 5 meters to 7 meters away from the power line. So my d phi, or my dA, sorry, is L dr. And if I want to make it a vector, then I can, and it's just going to be k hat, right? Because my area lies in my xy plane. So if I go x, y, and so from the right-hand rule, the area, the unit vector for the area comes out of the page. But also my B field follows the right-hand rule. So if I run my thumb along this direction, then my fingers coil in the direction of the field. So that means that the field is doing this, or approximately at the area it will be going into the page. So my B field is either minus K or plus K, depending on how the voltage is varying. And remember that our current, or as the current is varying, sorry. Remember our current is sinusoidally varying. That means that it takes values of plus I naught and minus I naught, so it's going back and forth. So at any time, the B field is going to be into or out of the page. Meaning that, but the point is that our d phi is just going to be our B field times our dA, because they're always going to be aligned. But I am going to use an absolute value here. Maybe I won't actually, just I'll let the sign kind of take care of itself. Yeah, I'll let the sign take care of itself, because it'll always be in the k hat direction, but the sign of omega t will give us our plus or minus sign. So that should be fine. Okay, so it's B dA, and so that's B L dr. And so now we want our total flux. So we need to integrate it from 5 to 7. So our flux is the integral of BL dr from 5 meters to 7 meters, which is just the B and L, and now filling in for our B field from above. So this is then the integral from 5 to 7 of mu naught I over 2 pi r L dr, which now we can bring out many of the constants. So mu naught I doesn't depend on the radius, and neither does the length. And so this is just integral from 5 meters to 7 meters of 1 over r dr, which is just a ln. So it's mu naught I L over 2 pi ln r from 5 meters to 7 meters. And so then this is just mu naught I L over 2 pi. Ln 7 minus ln 5, which comes out to be mu naught I L over 2 pi ln of 7/5. Just using the ln rules, which is if you subtract them, you can then subtracting 2 lns is the same as dividing by what's inside. And so then there's our flux now. Okay. So in this case, it's the current that's time varying, and it's going to result in our EMF. So now we can solve for our EMF. So our EMF is just minus n for the number of coils, d phi by dt, which is minus n, d by dt of all this. Okay. And then minus n. So our mu naught isn't time dependent, our L is not time dependent, this is not, and this is not. So it's just di by dt. So our I is I naught, our I is I naught sine omega t. So di by dt is just, so I naught is not going to, that's not going to be time varying. So it's just the sine omega t, and so that's going to give us an omega out front and a cos omega t. Okay, so then now our EMF is just minus n mu naught L over 2 pi ln 7/5 I naught omega cos omega t. And so it's asking for our peak value, and so cos omega t is giving us our time varying. So that makes it 60 hertz, but it goes between -1 and 1, and so honestly the only way we're going to get a max or a peak value is when this is equal to 1 or -1. And so our peak voltage is just going to be the rest of this, right? So n, so this is our max. And we want this to be equal to 170 volts. We have all of our values now, and so we can start to plug them in. So it's 10 turns of coil. I'm going to get rid of this equal. So there's 10 turns of coil, so n is equal to 10. Mu naught is a constant, so it's just 4 pi times 10 to the -7. And I better not drop units. 4 pi times 10 to the -7 newtons per angstrom squared. L is our length, which we are solving for, so I'll just leave it. Over 2 pi, ln of 7/5. And then our current is given as 55 kiloamperes, so times 10 to the 3 amperes. And our omega is 2 pi times 60 2 pi 60 per seconds. And now we can rearrange this for L. And so this all equals our 170 volts. So we can rearrange this for L and say that L is 170 volts over, I guess, times 2 pi. And then all over the rest of this. So 10, 4 pi times 10 to the minus 7 newtons per angstrom squared. Ln of 7/5. 55 times 10 to the 3 angstrom, not angstroms, amps. 2 pi times 60 per seconds. There we go. Okay, so we do have a little bit of cancellations here. So this 2 pi, we can dump that with, and that's pretty much it. Also, a volt is a newton per amp second is a volt. A newton per amp second, a newton meter per amp second is a volt. So I'm just going to actually erase the volt, write it in as a newton meter per amp second. And so our newtons will cancel. This amp is going to build up with this and cancel with that. So those will cancel. And then the per second over here will cancel, leaving us with meters, which is good because that's the answer we're looking for. And then if we run this all through on our calculator, we would get 170 over 13.953 meters, which is 12.18 meters. And so there we go. So the length of our coil to generate that 170 volts would have to be 12.18 meters. Okay. All right. So then, if we check our solution here, there is none. So it's obviously incorrect. So I guess I'll just say the solution is incorrect. Okay. So for the third one here, I'm going to do a couple circuits. So we've got A, and I'm just going to draw it and then fill in the extra information. So we've got R1, R2, and R3. And it says that if A is connected to B, through a 150 volt EMF, and we're given that R1 is equal to 150 ohms and R2 is 50 ohms. What is R3? I1 and I2, such that our total current is 1.00 amps. Okay, so the first thing we're going to need to do is, or the first thing we can do, I suppose, no, the first thing we'll have to do is compute our equivalent resistance in here. So our equivalent resistance is given as 1 over R is 1 over R1 plus 1 over R2, which is 1 over 150 ohms plus 1 over 50 ohms. And so our equivalent is 37.5 ohms. And so then we can compute our voltage drop across this equivalent resistance, as now if we were to redraw the circuit, we really just have A to B, and we have this R equivalent here, and R3, and we know we have 150 volts here, 0 volts here. And so then our voltage drop across our equivalent resistance, we have to drop our full 150 volts. So that means that our V1, and we know that we have 1 amp going through the full circuit, and 1 amp, and our total current, our current along a serial line has to be all the same, so that means our current here is 1 amp, and our current here is also 1 amp. So our V equivalent, so our voltage drop across the equivalent resistance, is given by Ohm's law as IR equivalent, which is just 1 amp, not an angstrom, times 37.5 ohms, which is 37.5 volts. And then we know, because we have to drop the full 150 volts, that our voltage drop across 3 has to be 150 minus 37.5 volts, which is 112.5 volts. So we have to drop the full 150 across the circuit. We know that we've dropped 37.5 across the equivalent, and so therefore we know that the drop across the resistor 3 will have to be this. And so now we can say through Ohm's law that our R3, I really want to make that a B, that our R3 is our V3 over our I, which is 112.5 volts over 1 amp, which is 112.5 ohms. Okay, so there's our R3. Now, to compute I1 and I2, we use the fact that we don't use that current is the same, but instead that voltage is the same in a split. And we know that the voltage drop in the equivalent resistance is 37.5. So that means for our split, the voltage drop across both resistances, R1 and R2, is 37.5 volts. Okay, so we know that the voltage drop here is 37.5 volts, and that the voltage drop here is 37.5 volts. So then we can easily compute the current, right? So V1 is 37.5 volts is equal to I1 R1. So then I1 is 37.5 over our R1, which is given as 150 ohms, which comes out to be 0.25 amps. And we know that V2 is 37.5 volts, which is I to R2. So then I2 comes out to be 37.5 volts over 50 ohms, which comes out to be 0.75 amps. The nice thing here is that our total current from our split, so I1 plus I2, should equal our total current, which is 1 amps. And if you look, if we sum it up, they do. So that means we didn't make a mistake. And there's everything that the question asked us to compute. Okay, so R3 is 112.5 ohms. And then I1 and I2 are their respective values. Okay, so if we check to the solution, equivalent resistance, 112.5 ohms, so there's our R3. Current through R1 is 0.25, R2 is 0.75, so that looks good. And I'll submit that.